Bear with us in our practical and exciting demystification of the different medium voltage drive topologies, their applications, their pros and cons, their concerns, and in the end of the video you will have a better understanding of the different kind of medium voltage drives and their application. We will identify key concerns for successful application of medium voltage drives and address them for each drive topology. Medium voltage drives help run the machines that keep your production going. These machines in many cases are critical to your operations. So before specifying or designing a power drive system, it is important to understand what your mission critical operations really need. These needs will be a fundamental part of the requirements of your medium voltage power drive system. The diagram shows a simple formula. If you want to maximize your revenue, you will need to maximize the uptime of your production process. Right from the start, you will need to get your reliability and availability right to allow for a maximum production runtime by minimizing your availability losses. You will also need to factor in the performance and quality losses to arrive finally at your fully productive time. Working safely and efficiently will maximize your gain. For sure, you will already have identified the mission critical machines of your production process. These machines are generally quite powerful and often they require a medium voltage power drive system. The reliability and the availability of that medium voltage drive system will be paramount for your mission critical machines. Are you looking for unbiased practical advice and practical ways to achieve maximum uptime of your mission critical machines? Do you want to make sure that your isolation transformer, your medium voltage drive and your motor are matched for your application in terms of reliability, efficiency, safety, quality and performance? But are you drowning in technical information, supplier biased opinions and no time to sort it all out? If said yes to any of these questions, then you're at the right place. Subscribe to our channel and get ready for clear and practical insights for your power drive system. This drivetrain diagram presents some key elements of concern. These are typical for medium voltage power drive system applications. The diagram suggests a left to right flow of the power from the grid supplied to the machine. In our video series, we will work our way from the right to the left. That is, starting from your machine through the drivetrain towards the grid supply, just as the green bar under the diagram shows. In this video, we will focus on the medium voltage drive. So what kind of medium voltage drive configuration do you need? Look to the drive as a black box converter. On the input side, you have the grid supply with constant sinusoidal voltage and frequency, and on the output you want again a perfect sinus with variable voltage, variable frequency this time. The ideal black box does not influence your grid supply and it delivers a pure sine wave to your motor. Now, what does it take to deliver such superb power quality and why does it matter? This is where the various types of medium voltage drive configurations called topologies come into play. The topology of the variable frequency drive combined with its filters determines the power quality of the power required for and delivered by the drive. Before getting into the nitty-gritty of topologies, let's get the basics right. We will for now only focus on the voltage source inverter, also known as VSI. In this basic diagram of a low voltage source inverter, there are basically three building blocks. Let's start with the rectifier, also known as the DFE direct front end, the intermediate circuit and the inverter. The voltage source inverter relies on capacitors in the intermediate circuit, and these capacitors create a decoupling between the rectifier and the inverter, and they compose also an energy buffer. In the third building block, often referred to as inverter, the DC voltage is recombined by the switching pattern of the IGBTs, insulated gate bipolar transistors, to a fundamental AC component with adjustable amplitude and frequency. In the topology slang, the terms pulses and levels are quite important. Back to the analogy of our drive as a black box, it is safe to say that the term pulses relates to the input side and the term levels refers to the output stage. Looking at our basic diagram, you notice that the output voltage will be created by connecting the plus and the minus at a switching frequency following a pulse width modulation pattern. This switching between two levels makes this a two-level drive. And yes, this is a three-level drive. Notice that the phase-to-phase output voltage of the three-level inverter is made out of 5 steps and is already looking much better than the two-level output voltage. Some manufacturers also offer a 5-level inverter, but it must be noted that if the 3 or 5-level inverters are to drive a standard motor that is not inverter duty, these inverters will require a sine wave output filter in order to reduce the common mode voltage and the voltage stress on the motor. These supplemental output filters can be of a significant cost and might also introduce performance restrictions on the power driver system. Moving further in our topologies overview and adding in more levels, you are now to discover the modular multi-level M2C MMC topology. Notice in the basic diagram of the modular multi-level inverter that the centralized DC capacitors are no longer present. Instead, we find capacitors for each power cell within the inverter part. The low voltage energy level stored in each cell results in an improved fault behavior as compared to other drive topologies. In the simplest case, such a power cell consists of 2 IGBTs and 1 capacitor bank. Medium voltage levels are obtained by adding together the outputs of multiple power cells. We can state that this drive delivers a superior sine wave output voltage and current, thereby eliminating harmonic heating and insulation stress on the motor, and reducing significantly the torque pulsations to levels lower than 1%. Next in our topology overview is the 2-level series connected multi-level cascaded H-bridge cells topology. What a mouthful. The multi-level cascaded H-bridge cells topology adds up the output of multiple low voltage power cells to obtain medium voltage levels. Each power cell is a simplified version of a standard 2-level PWM low voltage converter. Many applications, including low voltage drives, use low voltage IGBTs. They are manufactured in very high quantities. Medium voltage drives that utilize low voltage devices can take an advantage of rapid innovation cycles, exceptionally reliable components, and a sustained availability of spare parts. The result of adding up the output of multiple low voltage power cells is a high quality output voltage providing less than 1% induced torque ripple, no need for an output filter for motor cable lengths even up to 2 kilometers, a high reduction in common mode voltage, no derating on new or existing motor, no voltage spikes at the motor thanks to small output voltage steps, thereby indeed allowing the use or the reuse of a motor with standard insulations, ideal for retrofit. The integral dry multi-winding transformer provides for adaptability to available input voltage, clean input power thanks to the cancellation of the harmonics by the phase displacement in the secondaries. Multipulse inputs go from 18 to 54. Isolation from the grid, avoiding potential resonances and reducing impact from utility transients such as lightning and other equipment switching. This architecture, however, does not allow for regenerative operation or extremely quick deceleration. An active front-end version of this architecture is rarely economically viable. You can use this kind of drive for general purpose applications. For the more demanding applications with 4-quadrant and high dynamic response, you will need to look into the more advanced topologies. Let's go back to the analogy of our drive as a black box. We already stated that the term pulse relates to the input side. The rectifier bridge, connected to the capacitor, only conducts current at the peaks of the voltage waveform. That is when the AC voltage is higher than the capacitor voltage. So the AC input current waveform will contain bumps. In the basic diagram of a voltage source inverter below, you can actually see that we have 6 pulses in the rectified voltage UDC over one period of the mains voltage. In fact, when referring to a 6-pulse drive, we relate to a standard rectifier bridge containing 6 diodes, resulting in a 6-pulse DC voltage. The tree level depicted in this figure is made up of 2 6-pulse rectifiers supplied by a 3-winding transformer. We call this a 12-pulse in-feed. The secondary windings of this 3-winding transformer have a phase shift of 30 electrical degrees, thereby cancelling the harmonics, the 5th and the 7th, on the primary side. This 12-pulse in-feed results in lower line harmonic distortions. Indeed, the AC line input current of the 12-pulse drive looks already a lot better than the 6-pulse ones. The 12-pulse drive will generally not meet the requirements of voltage and current harmonic distortion imposed by current standards. Going for a higher number of pulses, such as 18, 12, 18, 24, or even 36, will further reduce the harmonic distortions, but this comes at a price for the rectifiers, the transformers, and at a higher footprint. An alternative to the architecture of characterized by the number of pulses is the active front-end AFE. Instead of a rectifier or a direct front-end DFE, we use basically a repeat of the inverter. The active control of the input stage enables a much cleaner input power and provides even for 4-quadrant operation. Finally, combining the modular multi-level version for AFE and for the inverter stage together realizes a high-performance drive with clean in- and output power. For now, we focused on the VSI and the key terms pulses and levels. Now let's take a step back and have an overview of the main topologies. The accompanying diagram categorizes medium voltage drive topology based on the conversion type. It is feasible to convert the constant supply voltage and frequency from the grid into variable voltage and frequency, either directly, that is from AC to AC, or indirectly, that is from AC to DC and from DC to AC. For the direct conversion, the Cycloconverter diagram clearly illustrates the concept of direct conversion. In contrast, the tree-level voltage source inverter exemplifies indirect conversion by first rectifying AC to DC and then inverting it into variable AC. Within the indirect conversion, which is the most popular one, you will find two types of converters: current source and voltage source inverters. And this brings us to the third level of the diagram, where we will zoom in on most of the converters. For starters, let's get back to our cycloconverter. A cycloconverter, or often referred to as CCV, is in fact a frequency changer without any intermediate DC link. The CCV converts AC power of specific frequency and voltage of the mains to different frequency and voltage. It is basically built by 6 anti-parallel connected thyristor bridges. It is mainly used for high power and low speed applications, such as direct drive applications, tube mills, mine winders, mine hoists, downhill and uphill conveyors, geared and ungeared horizontal mills, grinding mills, bucket wheel excavators, ship propulsion, gearless cement mill, steel roll mill and ore grinding mill. This converter offers high efficiency and bidirectional flow with low space requirements and great dynamic response. This all within a simple and robust structure for power ratings of 3 up to 50 megawatt. However, the operational speed is limited to 44% of the line frequency and the total power factor is rather poor, thereby often imposing the installation of filter circuits. Now let's move over to the current source inverter called CSI. The first one in the row is the Load-Commutated Inverter LCI. It is a single motor 4-quadrant drive for dedicated separately excited synchronous motors in the power range of up to 80 megawatts. This drive often requires a 24-pulse transformer to manage the input harmonics, and special attention is also needed to cope with a high level of torque pulsations. In industry, power plants and ships, the LCI drives machines such as blowers, sinter fans, pumps, wires, rod mills, extruders, refiners, compressors, tube mills, boiler feed pump, marine propellers, thrusters, shaft generators, test stands. These inverters are often used also as starting converters for blast furnace blowers, gas turbine sets and large synchronous motors on weak power systems. We conclude the current source overview with the self-commutated inverter. The self-commutated inverter is a pulse width modulated current source inverter. Because of the strong presence of input harmonics, this CSI requires an 18-pulse transformer or an active front end. The active front end design, composed by symmetrical gate commutated thyristors or SGCTs, uses a special PWM switching to regulate the current. The DC link uses inductors to regulate the current ripple and to store energy for the motor. The SGCTs in the inverter section are turned on and off to create a pulse width modulated output. The output voltage and current are close to sinusoidal, which is an important advantage for this kind of drive. Because of the high common mode voltage, the drive must be equipped with a suitable output filter. And this PWM-CSI is an inherent 4-quadrant drive and suitable for applications such as fans, compressors, pumps, chillers, cranes, hoists, extruders, ball mills, and in the power range up to 6 megawatts. This drive is quite popular in the retrofit applications where the existing motor is to be reused. While other topologies of medium voltage drive require an isolation transformer, the PWM-CSI version with an active front end can be used without. While this is a compelling sales argument, it is quite important to note that this configuration does not provide for the benefits of the use of an isolation transformer. These benefits include attenuation of the effects of transient on the grid, offering flexibility in selecting the supply voltage for the drive and the motor, reducing the maximum short circuit capacity, and enhancing system protection by isolating motor grounds from the main power distribution system. Before getting into the voltage source inverters, we need to explain two different topology classes. The main differentiator between those two classes is the common DC link. As mentioned before, the output voltage is made up of multiple levels or multiple steps. In the multi-level topology, the output is achieved through PWM switching of multiple levels in the DC bus. The 3-level and the 5-level VSIs are straightforward examples of this DC switching from 3 or 5 levels. Because of the possibility of using a common DC link, the modular multi-level voltage drive M2C or MMC is also considered part of the multi-level topology. The multi-cell topology is characterized using cascading power cells that are supplied by an AC voltage derived from the secondary of an integrated multi-winding transformer. So there is no common DC link in this case. In the topology of the multi-level voltage source inverters, we will start with the 3-level neutral point clamped drive. This voltage source inverter uses capacitors in the intermediate circuit between the rectifier and the inverter to create a decoupling and to function as energy buffer. The DC voltage is converted by the switching pattern of the IGBTs into a fundamental AC component with adjustable amplitude and frequency. For this kind of drive, the DC voltage is switched between 3 levels, plus, 0 and minus. Most of the time, this kind of drive is used in combination with a converter duty motor. The main reason for this is a rather high voltage rise in the output of these drives. In case of long motor cables, an output filter will be required to mitigate the risk of insulation breakdown caused by reflected wave voltage spikes. To reliably drive a standard direct online motor designed with standard insulation, the 3 and 5 level neutral point clamped drive will require a supplemental output filter. The basic configuration with a direct front end and a multi-winding transformer requires at least an 18-pulse transformer generally to comply with IEEE 519 standard. These kind of drives are widely used in general purpose applications such as pumps, fans, compressors, uphill conveyors, crushers, extruders, kneaders, mixers, excavators, high-pressure grinders, vertical horizontal mills, blast furnace blowers, the list goes on, propulsion, thrusters, boiler feed pumps, agitator presses, wire rod mills, forced draft fans, induced draft fan, and available up to 30 megawatts. This kind of drive can be fitted with an active front end to recover energy in advanced applications like rolling mills, test stands and downhill conveyors. Multi-level cascaded H-bridge cells. The integral dry multi-winding isolation transformer provides for clean input power thanks to the cancellation of harmonics by phase displacement. The remaining harmonic spectrum is lower than the level of an 18-pulse 3-level neutral point clamped drive. The multi-cascaded H-bridge cells topology combines the output of multiple low-voltage power cells to achieve medium voltage levels. Each power cell is a simplified version of a 2-level PWM low-voltage drive. This design delivers a superior sine wave output in voltage and current. The result is elimination of harmonic heating, insulation stress on the motor, and a significant reduction of the torque pulsations. Motor cable lengths up to 40 kilometers are supported, and this drive is widely favored for retrofitting general purpose 2 quadrants applications where the existing direct online motor, for example, is retained. It is available in power ranges up to 60 megawatt. Next in line is the modular multi-level inverter. The version with direct front-end DFE generally requires an 18-pulse multi-winding transformer to comply with IEEE 519. In the basic diagram of the modular multi-level inverter, you will notice that the centralized DC link capacitors in the DC circuit are no longer present. Instead, each power cell within the inverter part has its own capacitors. This design results in improved fault behavior thanks to the low energy level stored in each cell compared to other drive topologies. A basic power cell consists of 2 IGBTs and 1 capacitor bank. Medium voltage levels are achieved by combining the outputs of multiple power cells. The modular multi-level converter, or also called M2C or MMC, technology combines the benefits of cell-based converters and the flexibility of a drive with a common DC link. The M2C topology allows for a separate standard direct front end. This drive provides a superior sine wave output and voltage, effectively eliminating the harmonic heating and insulation stress on the motor and significantly reducing torque pulsations. For these reasons, this drive excels when the existing motor is to be reused for revamping purposes. These kind of drives are widely used in general purpose applications such as pumps, fans, compressors, uphill conveyors, extruders, kneaders, mixers, crushers, excavators, and the list goes on, high pressure grinders, vertical horizontal mills, blast furnace blowers, propulsion, thrusters, boiler feed pumps, agitators, presses, wire rod mills, forced draft fan, induced draft fan. In this configuration, the drive has no energy recovery capability. The topology can be equipped with an active front end to recover energy in sophisticated applications such as rolling mills, test stands, downhill conveyors, shaft generators, onshore power supply for a relative limited power range up to 16 MVA. This overcrowded table can be yours if you click on the download link inside the description below this video. We identified key concerns for successful application of medium voltage drives and addressed them for the mentioned drive topologies. Covering all use cases would make this video, already a long one, excessively lengthy. In this summary, we will focus exclusively on the topologies that are commonly used for general purpose applications, indicated in green. The general purpose applications do not require active braking. Think about a centrifugal pump that, when no longer driven by the motor, will slow down in a matter of seconds, or a fan or compressor that simply coasts down when ordered to stop. If the power flow reverses intermittently, that is, from the machine to the motor, an electronic braking unit can dissipate that energy into a braking resistor. Enforcing a deceleration ramp to a high inertia machine is a typical use case. Occasional recovery of this braking energy is in most cases not economically viable. Applications that do impose important power flow from the machine to the motor are classified under special purpose. In case of VSI topology, these applications require an active front end, allowing recovery of the energy to the grid for quadrant operation. However, the two-level series-connected multi-level cascaded H-bridge cells drive topology cannot provide for quadrant operation. On the other hand, on the other side of the spectrum, the PWM-CSI and the LCI are inherent for quadrant drive topologies. Typical examples for this use case are large inclined conveyor belt machines and test stands with the power drive system simulating the load of the tested machine. Another important use case in general purpose applications is the retrofit project where the existing motor is retained. You will need a topology that is preferably inherent motor friendly, such as the PWM-CSI, M2C or the two-level series cascaded H-bridge. The 3-level and 5-level neutral point clamp topologies will need a sine wave filter, adding costs and limiting the power drive performances. The Load-Commutated inverter will require a dedicated synchronous motor. Power defines technology. The application's power requirements will significantly influence the choice of topology. The load-commutated current source inverter is particularly suitable for power drives starting from 15 MW. The voltage source inverter's topology requires parallel unit configuration to achieve such high power levels, which compromises reliability and increases costs. The LCI can exclusively drive dedicated synchronous motors. The torque, pulsation and the input-output harmonics inherent to this drive configuration must be carefully managed. Reliability is paramount. Cell-based topologies including modular multi-level converter and the two-level series connected H-bridge cells utilizing low voltage components, redundancy N+1 and film capacitors typically offer superior reliability. The LCI technology is also highly reliable thanks to its robust thyristors and numerous proven applications in various fields. Finally, evaluate your drive manufacturer solution provider. As there is no such thing as one drive fits all, choose a vendor with a variety of drives, tailored to different applications, and ensure that they have references for successful power drive systems like yours. Prefer reputable manufacturer/solution providers with at least 10 years of experience and multiple field installed units. A large local installed base often means strong nearby service and support. Combine this with 7/24 remote support to significantly enhance your machine's availability. Ensure the manufacturer will be able to provide support parts and service for the lifespan of the VFD, which might be typically between 20 to 40 years. So what can you expect of us if you contact us? Well, you can expect impartial expert guidance in evaluating your power drive system in relation to key objectives of your mission-critical machinery: reliability, efficiency, safety, quality and performance. For each goal, we provide you with the right questions and support you in assessing the responses from your manufacturer, solution provider, EPC or OEM. Thanks for your attention, and please subscribe to our channel and turn on notification to receive updates on relevant videos. Feel free to contact us on our website proetic.com.